with the keynote session, and we'll have a coffee break afterwards. All right, so it's my great pleasure to introduce our final keynote speaker. That's Professor Giancarlo Ferrari Trecate. Professor Giancarlo is at EPFL, where he leads the group on dependable control and decision, which has an acronym DECODE, pretty cool. They work on machine learning, neural control, network control systems, hybrid systems, and microgrid applications. The group has been recognized by a number of Best Paper Awards, including one at ECC, the European Control Conference, CDC, the Symposium of the European Association for Research on Transportation. Professor Ferrari Trecate is also the founder and chair of the IEEE CSS Society in the Swiss chapter of that. He's also a senior editor of the IEEE Transactions on Control Systems and Technology. And today he's going to talk about performance boosting for nonlinear systems via stability-preserving neural architectures. We're looking forward to the talk. Thank you very much.
Thank you first for the... Yep. Okay, thanks. So thank you for the kind introduction. And I would also like to thank the organizers for inviting me here today, but also for all the work behind this beautiful conference. Really amazing job. And today I want to talk about improving the performance of nonlinear systems while preserving at the same time stability properties of the system we want to control. And you will see, for this purpose, I will use neural architectures. First, I would like to acknowledge the key contribution of my students. In the top row, you see former lab members who moved to their next job in academia and industry. And in the bottom row, current lab members who are very actively doing research on the topics that I will present today. The research has been motivated by the following common scenario in engineering. Often we do have system models and simulators of the system we want to control, but also baseline controllers guaranteeing some form of stable operation. And the problem often, rather than stability, it's really performance. To support this claim, let me mention here an ABB study in the process industry where it has been shown that 56% of the foundational loops in the process industry are underperforming. And a considerable percentage of these loops are really not closed loop, but open loop control. And there is another study conducted a couple of years in advance by Honeywell, where 26,000 industrial PID controllers were audited, showing that 68 of these loops performed in a suboptimal way. And performance is not affecting just industrial plants, but also systems we have in our labs. Here you see a beautiful robot built in the lab of Jamie Pike at EPFL. It's made of triangular elements with onboard sensing and actuation capabilities that you can compose like Lego bricks in order to obtain robots with different functionalities. And here you see a worker, but how the working is orchestrated? Well, thanks to a very smart distributed PID controller. But there is a price that you have to pay for using basic controllers, which is the following: the robot is slow. So this leaves a considerable room for improving the performance of the robot. And that's exactly, again, the topic of today's talk. I will talk about boosting the performance of a system without compromising stability. Okay, let me be a bit more formal about the problem that I call performance boosting. I want to consider a system which is nonlinear and stable or pre-stabilized. The example is here in the cartoon where you see 4 drones which are hovering about target points, irrespectively of the wind and thanks to the internal action of controllers. What they want to do is to close an outer loop in order to improve the performance of the system, which is represented here in the cartoon with the 4 drones doing a backflip maneuver. Now, in a more concrete way, what we want to do is to minimize a cost function, L, here, which is defined over a finite horizon, and L want to be an arbitrary cost, so not convex, not quadratic. Why this? Because I would like to include in L performance measures that are of interest for companies. For instance, in industry, you are interested in optimizing the economic factors or minimizing the energy consumption, or also promoting safety. And since I want to optimize a possibly highly nonlinear cost function, I also want to use a very flexible family of controllers, and to this purpose, I will include the neural networks in the controller. What's the key challenge? How to guarantee closed-loop stability. We know, even in the linear case, that even if the plant under control is stable, you cannot plug in whatever controller and hope to have closed-loop stability, right? And here I want to study the same problem, but in the full nonlinear setting. So, if I have to summarize in one sentence what you will see in this talk, I will show basically how to optimize over sets of neural policies which are stability preserving by design. Okay, so this brings me to the outline of my talk. First, I'll describe more in details performance boosting controllers, and I start with a theoretical result showing how to represent all stability preserving policies using a nonlinear operator. And then I show how to solve the nonlinear optimal control problem in the previous slide using neural policies in order to model these operators. The second part of my talk, I'll discuss the flexibility of the PB framework, basically showing that by shaping the cost and the operator in a suitable way, you can fulfill several control objectives and also cope with a variety of architectural constraints. And then I'll wrap up with some conclusions. So let me move to the first point. First, I need some notation. So in this presentation, I will consider nonlinear time-varying discrete time systems in the state space, as you see here, affected by process noise. The only non-standard point here is that I'm using the index T for F and W instead of T minus 1. That's just for notational convenience. Any standard nonlinear system can be written in this form. Here I'm using also controllers which are time-varying and dynamical. And the dynamics is here captured by the fact that the variable u at time t depends on the whole past history of the state. And often I will abstract away from time by using lower letters, bold letters for representing sequences and uppercase bold letters for representing operators, mapping sequences into sequences. This allows me to write this model in the signal space through the algebraic equations that you see here, that basically capture the closer, the infinite horizon evolution of the system. Just to be a bit more precise and to show how to build the operator F here, assume for the moment that the system under control is linear, and therefore F is defined by the two infinite matrices that you see here, where I have copies of A and B in the lower diagonal. What I've done is simply to copy and paste this equation at each time instant in order to obtain this representation. Little last point, I'm also embedding the initial condition of the system as the first element of the vector W, so I can assign this as an exogenous signal. Second point, stability. I'll focus on LP stability. An operator A is LP stable if it has two properties. First, it's causal. I assume causality by default. And second, it maps LP sequences into LP sequences. Remember, a sequence is in LP if it goes to 0 fast enough to have this sum, which is convergent. When p is equal to 2, here I am just measuring the energy of the signal. Okay? And for short, I'd use a calligraphic LP for denoting the class of LP-stable operators. I want to discuss stability in closed loop. So what does it mean that the closed loop is stable? If you close the loop, the only exogenous signal is W. So here I want that the operators, or the closed loop maps, from W to X and from W to U are both LP stable. That's the definition of closed loop stability, which is consistent with the definition of internal stability for linear systems. Good. Let me move to the main result. We want to consider control structures of this form, where here in the red frame you see a block diagram representation of the system. I call calligraphic F the system mapping the inputs W and U into the state sequence. Here you see in the orange frame the control structure that I propose, where I have a copy of the system dynamics followed by this operator M, which is a free operator in LP. Why it's interesting to consider this control architecture? Because if you assume that calligraphic F is LP stable, then choosing M in LP is necessary and sufficient for preserving closed loop LP stability. This means two things. First, if you plug in here whatever LP operator, you preserve closed loop stability. But second, even if you replace the controller K in the orange box with another one preserving closed loop stability, well, there is also an operator M implementing exactly the same controller. Now, if you want to implement the controller, you just have to go back from the signal space to the time notation. The summation node here is just there for reconstructing the noise W, so W hat is a reconstruction of W, and then you pass the W sequence to the operator M in order to compute the control input. I will show later how to translate this last step into a computationally friendly algorithm. Now, is this control architecture new? Not quite. We have replicated the model of the system into the controller, so we are considering an internal model control architecture that has been proposed by Economou, Morari, and Paulson in the 80s. But they were able to prove that this architecture is sufficient for preserving stability. Now we also have the necessity part. Second, the work that the architecture I'm presenting here is related to extensions of the Euler parameterization to the nonlinear case, a field of research that has been started by Charles Desor in the 82. There are several papers in this area, which are very nice pieces of theoretical work, but unfortunately they don't provide a way of implementing controllers, and often they don't even provide examples. Okay, let me highlight a weak point of the theorem. We have a necessary and sufficient condition if we plug into the controller exactly the model, the real model of the system. But what happens if we have model mismatch? So we have a nominal model F hat here, and the real system is F hat plus a mismatch delta. You can still preserve stability by detuning the LP gain of the operator M. We have a precise bound. If the LP gain of M is less than this term, which is mismatch dependent, then you have a closed loop stability. Now, if all the blocks that you see in the diagram are linear, you can compute this quantity. Otherwise, if you have fully nonlinear systems here, it can be difficult to get the precise gains, but the message is if you detune the gain of M enough, you still have stability. Okay? And the other point is that this inequality is non-conservative in a sense, non-conservative in a sense, because when delta is 0, there is no mismatch, the upper bound goes to infinity, and you recover the necessary and sufficient condition of the previous slide. Okay, so let me now show how to implement the operator M using neural networks. As I told you, for stability, you want to choose M in LP, and optionally, you want to put an upper bound to the LP gain of M, but the problem is that MLP is an infinite dimensional space, so optimization over LP is intractable. And for this reason, I resort to class of models that I call optimization-oriented. So these are models of the operator M with two properties. First, we want M to be described by a dynamical system with its own state x tilde, and we want to embed in the functions G and H possibly deep neural networks, but still described by a finite number of parameters that we collect into theta here, okay? And second, we want the model to be freely parameterized, which means that for any value of theta in Rd, you want that the functions G and H associated with theta provide a stable operator. While this, because if you have this property, then you can do unconstrained gradient descent in Rd in order to optimize your operator, and unconstrained gradient descent is much cheaper than the corresponding constrained and projected counterparts, okay? So this is what enables here really the use of deep networks before hitting computational limits. And another advantage is that you can use standard machine learning pipelines for optimizing this kind of models. Now, do we have optimization-oriented models of LP operators in the literature? Yes. If you are interested in bounded input, bounded output stability, you want to consider the L infinity case, but then any neural network, static or recurrent, with bounded outputs implements an L infinity operator. If you're instead interested in L2 stability, so you want states converging to 0, then there are different solutions in the literature, ranging from static neural maps, proper feed-forward neural networks, to recurrent neural networks, so dynamical systems. And there I would like to mention the recurrent equilibrium networks produced by the group of Jan Manchester, but also other solutions based on Port-Hamiltonian systems or structured state-space models. And to give you a feeling of the challenging in deriving free parameterizations, let me discuss the content of this paper. So how to obtain free parameterization of a structured state-space model with a prescribed L2 gain, upper bound. Okay, so what's a structured state-space model? Probably you're familiar with these models. In machine learning, they are very popular in LLMs. They are seen as the next generation of transformers in a sense. And here you see the block diagram of an SSM, a little bit simplified compared to the original proposal by the papers down here. The SSM I'm considering is composed by an encoder, which is just a rectangular matrix, a decoder, again a rectangular matrix, and then internal state-space layers which have identical structure but different parameters. And zooming in into an SSL, you find a linear dynamical system, a Lipschitz nonlinearity with parameters xi, and a skip connection, okay? So overall, here I am representing an operator from W to U, and the natural parameters are the matrices A, B, C, D in the SSLs, together with the parameters of the Lipschitz nonlinearity, and then also the scalar entries in the encoder and the decoder. Okay, now the problem is how to provide a free parameterization of this model by realizing also a model that has an L2 gain less than a prescribed quantity, which is gamma bar. And of course, the natural parameters are not a free parameterization because you can choose the matrix A, I as you want and generate easily an unstable system. Okay? So, to discuss the derivation of a free parameterization, let me focus on the linear part of the SSL only. So here the sub-goal is to obtain a free parameterization of LTI system with a prescribed L2 bound gamma bar. And as we have shown in this paper, you can proceed as follows. You consider the following free parameters. The first two are scalars. The others are matrices of suitable dimension. And then you do the computations here in the block 1. I'm not entering in the details, but this produces quantities that are then used for getting the matrices A, B, C, D of a linear system. And the result is the following. We have a complete parameterization of square LTI system with a prescribed L2 bound. Complete means that up to a zero measure set of systems, we capture all the system that we want. Okay? And then it's enough here to complement this free parameterization with existing free parameterization of Lipschitz multilayer perceptron and also free parameterization of the scaffolding, that's easy, in order to obtain a full free parameterization of the SSM. And the details are reported in our paper down here. Okay, maybe the last point is the following. Here, the algorithm that you see defines a mapping which is differentiable almost everywhere. And therefore, when searching in the space of free parameters and trying to optimize the SSM, the nonlinear transformation that you see here enters in gradient descent very easily because automatic differentiation can backpropagate through them. Okay? Good. So let me now put everything together. How to design concretely performance boosting controllers. We want to solve this nonlinear optimal control problem. And the first thing that we did is to get rid of the stability constraint by focusing on internal model controllers. Now, still we have seen that we cannot search in the space of LP operators, so we replace M with an optimization-oriented model. But also, the average here is intractable, so we want to replace it with an empirical average based on noise samples. Okay? And now what you have here is a standard problem in machine learning. I want to optimize a data-dependent cost subject to a recursive computational structure. Then you can backpropagate through it. The structure here is recursive when you unroll in time the dynamics of the system and the controller. And this method is known as backpropagation through time. Okay? So you can use a TensorFlow or PyTorch for finding your controller. Of course, there is a problem, which is the following. If you use here too few samples, then you are overfitting your controllers to the noise realization that you have seen. And this can be not ideal when deploying the controller in the real world, where the controller is subject to new realizations of the noise. But then we also developed another method which is based on pack-based theory. Here the idea is to define a prior distribution over the controller parameters, the parameters of the operator M, and then use noise samples and the cost in order to obtain a posterior distribution over controllers. And in this context, design means sampling from the posterior. Not always easy if the posterior is very complex, but the advantage is that now we can incorporate prior knowledge about good controllers by specifying the prior distribution, and also we can mitigate overfitting and obtain generalization bounds. So upper bounds with high probability through this cost, which is the true generalization cost, we cannot compute. Good. Let me now move to some examples. And I'll start considering a very simple one, the corridor problem. We have two robots, orange and blue. These are point mass dynamics. There is just a small nonlinear component, which is a nonlinear drag. And we want to stabilize the robots on the corresponding targets while avoiding collisions and also collisions with the obstacles. Now, the performance boosting framework enables a separation of concern principle if you want to perform a design from scratch, which means the following. First, you care just about stability. And we can stabilize the robot to the targets using a very simple baseline controller. It's a proportional controller mimicking the presence of a spring connecting the endpoint to the initial point. Okay? So you see here, you have collisions, also overshoots, but we don't care about this. We compensate for this phenomena in the second stage, where we add a control component UT here that we define through performance boosting. So now we obtain a neural controller that tries to optimize this cost, where we penalize the energy for reaching the targets, collisions between the robots, but also collisions with the obstacle, the green parts here in the plot. And in these two terms, we use barrier-like functions to promote the absence of collisions. And when you close the second loop, then the robots learn how to solve the corridor problem and to stabilize at the destination. An interesting point here is that closed-loop stability is guaranteed despite early stopping of the training, or even if you end in a local minimum, you never lose stability. And that's exemplified by the clips down here, where I stopped the training iteration at 25%, 50%, 75%. Of course, performance is worse, but stability at target is never lost by construction, because the iterates of gradient descent are all in the space of controllers that preserve stability by design. Okay, so let me give you another example where we want to stabilize the 3 drones here to the corresponding targets, avoiding collisions and obstacles. But in this case, we used Mujoko models. We didn't derive the state space equation of the systems, and specifically, we used the Bitcraze Fly 2.0 models with a baseline proportional derivative controller for target reaching. And this is the work of my colleagues Christian Brugnara and Dario Piga at the Institute Dalle Molle in Switzerland. What they did is really to plug the whole simulator in the loop for design. So now we can backpropagate through the simulator and obtain the operator M that tries to stabilize the drone and avoid collisions. And after doing this, that's what you see in the simulation, so the drones are really capable to go to the target in a stable way while avoiding collisions. So we can backpropagate through differentiable simulators, and this is thanks to the fact that the framework allows for fully nonlinear time-varying models. Last example, now it's a real example, and for this we use the bumper car platform that I have in my lab. So that's a platform we have developed with the support of the NCCR Automation, which is a big project about automation and AI in Switzerland. And what we did here is to take bumper cars from a Luna Park and engineer them in order to have fully autonomous vehicles. That in general we use to demonstrate to the wide public how control can be very useful for promoting safety in autonomous driving. That's the game here played by my students. But today I'll use the bumper cars in order to discuss the properties of performance boosting. So we need a model, and to this purpose we have developed a digital twin of the bumper car, which is composed by a first principle non-holomic model complemented by a neural network part. Why? Bumper cars have a wide steering angle, more than 100 degrees. And during extreme maneuvers, there are also a rubber part at the bottom of the car that touch the ground. These are very difficult contact phenomena to capture using first principles. So that's why we use the neural network model here. And what we did is to take this model and to use it as a baseline here in order to compute the operator M, in order to solve again the corridor problem, but now with a much more complex models. So we want to stabilize the two bumper cars to the corresponding targets and avoid collisions, also collisions with the obstacle without the two little chairs that you see here. The baseline controller is just a simple pursuit controller, and as you see, the cars bump into each other. They also try to reach the corresponding target, but this is not possible because they cannot cross each other, so in the end, they land in a random point. While if you use performance boosting, they learn how to give way in order to avoid collisions, obstacles, and get there, get at the destination. Not only, but if you start from a different initial condition with a different heading, then you have a different behavior. In this case, the car on the right waits before going to the destination. So the policy is really dependent upon the initial condition of the system. Okay, so let me now discuss the two sources of flexibility of the framework, which are the cost function and the operator M. Now, the cost function appears in the optimization problem, and now we can choose it with a lot of flexibility, as people in reinforcement learning do all the time. And therefore, you can promote a variety of behaviors by choosing the function in a suitable way. For instance, you can enhance classic time-based performance metrics, like reducing the settling time, improving the decay rate, reducing the overshoot. This can be done by shaping L in a suitable way. But you can do more. You can also promote probabilistic safety certification by introducing risk-aware terms in the cost that basically try to optimize the probability that the state lies within a target region when the noise is stochastic. For promoting safety, you can also use invariance. Here we have set the cost in a way such that the system is confined in the light, in the region with the light background. And the last example here, it's about designing a cost that enables the fulfillment of a complex mission. And that's the case I want to describe next. In this example, we have the two robots that we have seen before, and the task specification are as follows. We want to avoid collisions, but the blue robot has to visit the point A first, B second, C third, and stabilize at destination. The orange robot, different order, first C, then A, then B, and stabilize at destination. So how can you promote the mission by designing a cost? There is a solution. You can use linear temporal logic, right? And there is an automatic way to translate a linear temporal logic formula into a cost, which is complex, would take probably a whole slide if you write it down, but still we have a candidate. And now for controlling the system, we do as before. First, we design a base controller only for stabilizing robots at destination without caring at all about the mission. And then, by optimizing the cost you see here, you obtain the desired behavior by closing the outer loop due to performance boosting. So here we try to promote the absence of collisions, the fulfillment of the mission, and also we try to minimize the total energy spent by the robot, used by the robot. Okay, let me now move to the other degree of freedom we have, which is the operator M. We can choose M in LP, but the class of LP operators is very rich. So we can use this flexibility in order to satisfy control architectural constraints or to achieve specific control objectives. And here you see 3 examples. First, we can design operators with a distributed structure. So local operators interconnected by a communication network. The real challenge here is how to derive a free parameterization of interconnected operators. But if you can do it, then you can associate a local performance boosting controller to each robot and minimize the cost, which is stabilizing the robots at the targets, and at the same time tries to minimize the formation error in reaching the targets. And so this is a truly distributed controller. Second, you can synthesize M online as time goes on in using, let's say, a receding horizon approach for solving the optimization problem that I've shown before. And that's very useful if you have, for instance, moving obstacles, or if you have sudden spikes in the disturbances affecting the robot. And last, you can embed in the operator M contextual information, here in the form of the destination points that now are specified at runtime. And in the last part of my presentation, I would like to describe a bit more this last case. So how to embed context information in control loops. Now, what's context information? To me, is any useful environmental signal that is sensed and can be used in the controller in order to improve the control action. We want to do this while preserving stability. Examples of context: if you have a robotic system, you might have dynamic obstacles that you might track, but also camera feeds, possibly processed through AI pipelines, and even fault signals if you have some fault in the component of the system during deployment. And you will see an example of this later on. Okay? And now the point is how to use, I have here an operator which is in LP, but now using also context. Context is not necessarily an LP signal, so it's not necessarily a vanishing signal, right? And in order to include context in the operator M, we propose the following factorization. We write M as the product of 2 operators. The first is an operator in L infinity, so a bounded operator that gives as output at every time instant a matrix and depends on the context. The second operator gives as output at every time instant a vector, and here we take the time product of the sequences. Okay? So this defines a vector envelope, and we can also make this operator dependent on the LP part of the context, so context signal that vanish over time. Now, you may think that this representation is a limitation, but not really, because we have shown that you can represent an operator set dense in LP through this factorization. So roughly speaking, this means that any operator that has that is relevant for engineers can be written in this form. Let me also give a bit more of intuition about why using context is so important. I'm considering here the control input in 2 dimensions. So a vector with 2 components can be represented in polar notation. And I'm using here an operator MP, giving a scalar and taking the absolute value for the magnitude component, and a generic causal operator here that gives me the angle. And now I can introduce context in here. That's the M infinity part in the general description. So I can make the direction of control dependent on the context. And that's why introducing contextual information can be very useful in control. So let me give a couple of examples. First, Here you have a robot. I want to stabilize the robot to the target, but also in the process, the robot has to cross a gate which is randomly switching position until a time which is unknown to the robot, okay? And for solving this problem, we develop a controller using this context. The context includes the position of the gate, how close the robot is to the upper and lower walls, that tells the robot when to act to avoid collisions, and third, the time since the last gate switch that tells the robot how stable the gate is. And here you see two simulations. In the first one, a performance boosting controller and also the baseline controller in gray without using any form of context. And in the other panel, what happens if you use context without changing the total number of parameters. So without context, the robot basically never learns how to cross the gate, so the success rate in deployment is 18%, while if you introduce context, now you see that the robot learns to slow down until the gate has stabilized and then cross the gate and go to the destination. Let me also highlight here a very important application of context, which allows us to generalize performance boosting from stability preserving to reference tracking preserving controllers. So first, let me tell you what does it mean to boost the performance of a reference tracking controller. Now, the base system we consider here is the following. We have a system equipped with a local reference tracking controller, and the goal of this controller is to drive the state of the system, the internal state X, to a reference that belongs to a given reference class, XREF. Formally, when U is equal to 0, U is the performance boosting channel that we are not using yet. And when W is in LP, we want that the tracking error is in LP. That's the formal definition of tracking. And the common case is when we want to track here a constant reference, and so we use an integrator in the control loop in order to have this property. Now, for boosting the performance of the base reference tracking system, we put the system in the pink box up here. Again, take a copy of the system and put it in the controller, followed by an operator, calligraphic M. But now the difference is the following. We supply M with the reference signal, and the reference signal is not necessarily in LP, it can be also a constant signal, okay? Still, we have the following result. Assume that M, the operator here, has the following properties. The output U is an LP signal for all possible W's in LP, but XREF in the set, capital XREF. Then the blue frame represents all and only controllers that preserve stable tracking, okay? But now M is not an L2 operator. It has to produce an LP signal even when using context signals which are not vanishing. So how to design this operator? Well, that's easy. We use the parameterization presented in the previous slide, and we embed the reference signal as context. So we split M into the M infinity part, XREF dependent, and an LP part. Okay? And to conclude, let me present an application of the framework in an even bit more complex scenario where we want to do at the same time reference tracking and also compensate for faults. So here I am considering an active front-end drive system, which looks like the one you see here in the picture. And here you have a block diagram representation. So the goal of the system is to take power from a medium voltage grid and feed a motor that has to track a velocity reference for the attached driveline, which is represented here. Okay? The electrical and mechanical parts are coupled through the DC link, which acts like a power buffer and partly decouples the two sides of the system. So the DC link gives power to the motor when needed, but can also transfer power back to the grid when is overcharged. Okay? Now, we have baseline controllers for these industrial systems, which are PI loops with saturations, feed-forward actions, and the goals of these basic loops is to track three references: the angular speed of the driveline, the voltage of the DC link, and the reactive power sent back to the grid, in spite of the disturbances, which are the load torque applied here, and the deviation from the standard three-phase voltage that you have in the grid. Okay? So, in spite of these controllers, there is a critical scenario. You might have grid phase loss. And when you have this phenomenon, which is rather frequent, then the voltage across the DC link goes outside safety bound, but this is very critical because this triggers immediately the shutdown of the plant, which implies also financial and productivity losses. Okay? So next I will show how to preserve the tracking properties of the basic PI loops while also improving the faulty behavior. And what we have done is to use the reference tracking PB scheme introduced before, and now we have plugged the model of the system here for control design, and a bit more realistic simulator here for obtaining simulations, right? Now, note that the subsystems are fed with the reference signals, but also the disturbances, which are measured, right? These are torques and voltages, so easy to measure. Now, how to design the operator M? Using the splitting method I've described before. So we have an M infinity part, an M2 part, and we make the M infinity part dependent on the disturbances, but also the voltage across the DC link and the grid current. Why? Because these signals, are heavily affected by a fault. So basically they tell the controller how to counteract a fault. These are also signals which are not in LP. VDC generically doesn't go to zero, so we embed them in the M infinity part of the operator. We also use here a fault indicator in the M2 part of the operator, which is there for waking up, let's say, the operator when there is a fault, because the M2 part tends to produce a signal that goes to zero otherwise. So what about the cost? Here we optimized a cost in which we penalize tracking error for the DC voltage, the DC link voltage. And also we put barrier function terms for keeping VDC and the grid current within prescribed limits. And after designing the controller, we obtain the following result in a scenario where first we have a total loss of phase C of the grid, and then later on 60% reduction loss of the same phase. So these are faults that happen in this part of the plant. And down here I'm representing now the behavior of the DC link voltage under two control actions. First, when only the baseline controller works, that's the orange profile. And second, baseline controller with reference tracking performance boosting, and that's the blue line. First, when we have a total loss of the phase, you see that the base controller, the DC voltage under the base controller violates the lower bound for more than 3 100 milliseconds, which triggers the shutdown of the plant, while performance boosting allows to obtain a voltage which doesn't violate the bound, but also it's closer to the reference, which is 5,000. And for the second fault, okay, in this case, even the PID loops are able to keep the voltage within bounds, but performance boosting keeps the overall voltage closer to the reference. And this is achieved because we are using neural controllers, so nonlinear controllers, that can shape the frequency content of the grid current in a very subtle way, something that is very difficult to achieve by using just linear loops. Okay, so this brings me to the conclusions of my talk. First, I try to convince you that performance boosting is really a flexible framework for improving the performance of a nonlinear system. And also, this framework enables a separation of concerns. So first, let's care about stability, even with a simple controller, and then optimize for improving performance. And the second message is that we have now tools in the literature for implementing this controller, for training these controllers, because we have a free parameterization of stable neural networks that allow searching over stability-preserving policies. Second, we have several extensions of the framework I didn't mention today in the interest of time. For instance, extension to output feedback controllers, methods for guaranteeing safety in a rigorous way, not just promoting safety through the cost, but also recently we have developed a dual parameterization. So we have parameterized all the plants that are stabilized by a given controller, which is very useful for developing new closed-loop nonlinear identification algorithms. And finally, in terms of research, of course, the main point here is that we need a model of the system, so we are studying how to lift the framework to the full data-driven setting, but also we are considering several applications together with our colleagues. For instance, applications to district heating networks together with Polytechnic of Milan, applications to microgrids in the framework of this project sponsored by the Swiss project that I've mentioned before. And also we are studying, trying to understand if and how performance boosting can be used for improving so-called artificial pancreas systems, where you have here an insulin pump that has to react to measurements in continuous time of the glucose that is in the blood of the patient. So we want to understand whether we can build upon these basic loops that are available already today in order to improve the quality of life of the patient. And this brings me to the conclusion, so thanks a lot for your attention. I'll be happy to take any questions.
Please, let's have some questions.
If I understood correctly, your parameterized class of controllers is a stateful, right? Like the state space model controller. Is this what you used for calligraphic M?
Yes. What I've shown today is state feedback.
Okay.
We also have output feedback solutions.
But does the controller itself have like an internal state?
Yes, it's a dynamic controller, like a PID, right?
So I mean, if this were certain classes of cost functions, you would not necessarily need that for optimality, right? Like if it was like Markovian dynamics, you would ideally want your controller to just be a function of the observed state and not to have an additional internal state. Is there any way to parameterize the set of controllers with that restriction?
Oh, yes. Yeah, I mean, it goes under the banner of choosing the way of parameterizing the operator M. Even a stable transfer function is a parameterization of M, right? Even a constant controller is the legitimate LP operator. So yes, you can simplify the controller if you want and if it's needed by your application.
And it could still be used within this general framework?
Yeah, absolutely. I mean, it's one of the possible candidates among all possible LP operators. Yes?
Thank you.
questions? Okay, I'm back there.
Thank you for the great talk.
Thank you.
I was wondering about the objective and if you have like some intuition how you design that. I guess like you had this LTL example and then you also had like other examples. So is this, just like control intuition or like, how are you thinking about this?
Yeah, thanks. That's a great question. Actually, it's the same as designing an objective for an RL problem. We don't have any formal method. We have seen yesterday in the talk by Alessandro Abate how to replace a complex cost with other solutions. That's a possibility probably that we can integrate also with this framework. But I think a lot of research is needed both in machine learning and control in order to understand how to specify in a meaningful way the cost. I can tell you that in applications that we have, choosing just the right unit measurements in the cost term makes the whole of a difference because it changes the optimization landscape and makes the control design very much easier.
Maybe one last question.
Yep.
All right, over there.
Hi, Gianni. Thanks.
Yep.
Great talk.
Thank you.
One question on uncertainty. So all of this is very deterministic in a sense. So I'm thinking whether you have ways of extending this to, say, capturing also uncertainty in a probabilistic way.
Thanks for the question. So stability, as I've defined today, LP stability, it's a kind of basic property that qualifies a control algorithm as reliable, as opposite as algorithm that destabilize the system, right? But still, it's just basic stability. So you might want to guarantee other properties on top of this, especially when you have stochastic disturbances. We are studying solutions based on a distributionally robust optimization to be included in the process because we deal with an optimization process in the end. But I mean, it's very much uncharted territory. So any contribution would be very much appreciated in this direction. Yeah.
Right. Let's thank Professor Ferrari Trecate again.
Thank you.
All right. Enjoy the coffee break. We'll be back here at